Math 1332, Chapter 10, Probability and Counting Techniques, Section 1, Basic Concepts of Probability, Video 3, Empirical Probability, the Law of Large Numbers. A car manufacturer wants to assess the quality of cars rolling off an assembly line. The supervisor selects 50 cars randomly over the course of 3 months and tests each according to industry standards. It is discovered that 3 of the cars do not meet industry standards. Based on these observations, what is the probability a car coming off that assembly line does not meet industry standards? I wouldn't overthink this one. 3 out of 50 cars observed did not meet industry standards. So is the probability 3/50ths or 6%? Yes and no. We can't call this a theoretical probability because we do not have access to the entire sample space of all cars that have been or will be produced on that assembly line. However, based on past data that we observed, we can say the empirical probability is 3/50ths or 6%. For theoretical probability, the probability is based on events in sample spaces without the need to actually conduct a probability experiment. But sometimes this is not plausible for a variety of reasons. For example, maybe the entire sample space does not exist yet, as in the case of cars that will be produced on that assembly line in the future. Or maybe the sample space is too large to accurately enumerate, such as all possible ways for a chess game to be played. When theoretical probability is not appropriate, we can use what is called empirical probability. This type of probability is based on observing past data. In the case of the cars on the assembly line, we use past data, 50 cars, 3 of which did not meet industry standards, to make a prediction about future production, that 6% of cars produced in the future will not meet standards. Here's the formal definition of empirical probability. Suppose an experiment is repeated n times. So the letter n is representing the number of times we repeat an experiment. And the event E is observed f times. The letter F is for frequency. Then the empirical probability of event E is simply f over n. How many times did we observe what we were looking for divided by how many times did we repeat the experiment? The main difference between theoretical and empirical probability is simple. When calculating theoretical probability, the experiment does not need to be conducted. Probabilities are based on the number of outcomes in an event and in a sample space. When calculating empirical probability, the experiment must have already been conducted. The more times, the better. There is a relationship between empirical and theoretical probability. Let's see if you can deduce that relationship. A casino pit boss suspects a worker is using loaded dice when his friend comes to play craps. They're working together to cheat the casino. To test this theory, the pit boss confiscates 1 die. He rolls it multiple times and records the number of times 5 shows up. He knows the theoretical probability of rolling a 5 is 1 out of 6, or about 16.67%. A, after 10 rolls, the number 5 showed up 3 times. Calculate this empirical probability. All right, well, 3 out of 10 times, the die came up a 5. That's 30%. Notice that is significantly larger than what is expected, theoretically. After 100 rolls, the number 5 shows up 19 times. Calculate this empirical probability. Well, out of 100 rolls, the number 5 showed up 19 times, and that's 19%. That's still a little higher than the 16.67, but notice that it's closer than the 30% was. After 1,000 rolls, the number 5 showed up 165 times. Calculate this empirical probability. 165 divided by 1,000. Turn it to a decimal, move the decimal place two places to the left, and you get 16.5%, which is really close to the theoretical probability. So should he be worried about the die being loaded? Well, what some people will do is repeat an experiment a small number of times, like 10 times, come up with something like 30% right here and say, look, I got 30% of the time. It's only supposed to come up that percent of the time. Gotcha. But the problem is, in the short term, anything can happen. I could have rolled the 10 times and not got a 5 at all and gotten 0%. And I couldn't get exactly 16.67% anyway when I rolled 10 times, because regardless, it's going to be 0%, 10, 20, 30, 40, etc. But as he rolled more and more, the probability was getting closer to what it was supposed to be. So should he be worried about the die being loaded? Well, the short answer is no, but the reason is something called the law of large numbers, which establishes a relationship between empirical probability and theoretical probability. Suppose a probability experiment is repeated n times, and the empirical probability of some event E is calculated. As n gets larger and larger, the empirical probability approaches the theoretical probability. Translation: if the theoretical probability is correct, then the empirical probability will get closer and closer to it as we repeat an experiment over and over. When n equals 10, we had the probability the event was 30% back here. When n equals 100, we had the probability of the event being 19%. And when n equals 1,000, we had the probability of the event down to 16.5%. The empirical probabilities are approaching the theoretical probability, 1/6. They're about 16.67%. If watch very closely what's about to happen. If the die were loaded in a way that affects rolling a 5, then the empirical probabilities would not be approaching the true theoretical probability of 16.67%. Take that parentheses out there. Let me say that again. If the die were loaded in a way that affects rolling a 5, then the empirical probabilities would not be approaching the true theoretical probability of 16.67%. The empirical probabilities are approaching the theoretical probability. That sounds like two premises. Oh my gosh, blast from the past. Premise 1, if the die were loaded, then the empirical probabilities would not be approaching the true theoretical probability. Premise 2, don't look at all that. Premise 2, the empirical probabilities were approaching 16.67%. Can we draw the conclusion the die was not loaded in a way that affects rolling a 5? We actually can. Why? This argument forms the law of contraposition, thus its conclusion is valid. Look at me sneaking in chapter 3, symbolic logic stuff in there. The point I'm making is this. Besides the fact that I did make a connection between what we've done previously, what we're doing now, the law of large numbers says if your theoretical probability is correct, then your empirical probabilities will approach it as you repeat an experiment over and over again. So does this, that's not what I needed. Okay, come back to that in a second. But we never really answered the question, should he be worried about the die being loaded? The answer is no. Because the theoretical probabilities are approaching it. Well, let's put it this way. If it was loaded, then the empiricals would not be approaching the theoreticals, but the empiricals were approaching the theoretical. Therefore, it was not loaded. So no, he doesn't have to worry. In the short term, anything happened, but over the long term, that's where the numbers catch up. Just remember, both theoretical and empirical probability answer the same question. What percent of the time do we expect an event to happen? The main difference is theoretical probability is based solely on sample spaces, events, and their cardinalities. No experiment is actually conducted. By contrast, empirical probability is based on calculating the percent of the time an event occurred after conducting the experiment multiple times. The law of large numbers says the more we repeat the experiment, the closer the empirical probabilities get to the theoretical probability. One last closing comment. Theoretical probability is like trying to predict the future. We're not going to conduct an experiment, but if we did, this is what we predict would happen. Empirical probabilities is like describing the past. We already conducted an experiment, and this is what we saw. So theoretical probability, predicting what will happen, the future. Empirical probability, describing what already happened, the past.